her name is Ja Li. I hope I pronounced this right. I've done some training before this. So she is head of R&D Cloud, AI, and machine learning at Google. And before joining Google, she was head of research at Snap. And she got her PhD from Stanford. And aside from her many roles at Google and before that, she is also serving the scientific community in a number of roles. So for example, she's program chair of the ACM Multimedia Conference and many others, which I'm not going to list. And also her technical contribution has been recognized by a number of awards. For example, Master Inverter Award for Innovation in Computer Vision, Machine Learning, Artificial Intelligence, and many others, which again, I'm not going to list all. But the most interesting one for me at least is she was listed as one of the secret power player who runs Snapchat by Runner Insight 2006. So that's really interesting. So saying that, let's welcome her.
Is this one? Yeah. Thanks for the introduction. It's my pleasure to be here. Today I'm going to talk about from insights to solutions, an invitation to the AI journey. AI is advancing quickly with its impact everywhere, from transportation to finance to communication. AI is making huge change to transform business. However, the success stories tend to be found in tech-savvy industries. What about the world beyond Silicon Valley? Many traditional industries like manufacturing, agriculture, and healthcare still are facing a lot of repetitive and sometimes dangerous work. AI could make this process a lot more efficient, and humans can be freed to focus on what they do the best. But there is a gap between the AI experts and these traditional industries. Just like many industries outside of tech might not know much about AI, those of us working in AI know very little about them. As a result, this potential haven't been achieved. AI is a nascent space full of potential, but turning all these potential into real solution is not easy. Throughout my career as an AI technologist, I've had the opportunity to participate in this journey firsthand. I'd like to share today about how it works. For example, how insights could generate interesting machine learning problems, and how data could be organized and processed to represent these problems. And based on the data, how would algorithms be innovated to tackle these problems? And finally, how would we be able to build robust and scalable solutions to solve real-world problems? Then I'd like to talk about how to open up this process to many other industries, allowing AI to solve entirely new problems. As a computer vision researcher, my first encounter with AI problems was a big one, to teach computers how to see. As we know, an image is worth 1,000 words. It may sound simple to us humans because we can easily perceive and understand our visual world so naturally. For example, in this photo, we can see a dog is having a birthday party, and 2 kids are serving cakes to it. In a simple glance, as humans, we can perceive objects, events, scenes, and activities. These ability came to us so natural that we take it for granted. But this is actually a remarkably challenging problem for computers. Let's talk about how do we teach computers to see. Start with a very basic task, object recognition. Basically, we want our computers to read this image as input and tell us there is a cat in it and there is also a ball of yarn in it. Now, our question is, what kind of data we should use to solve this problem? In order to represent the interesting machine learning problems that we want to solve, AI data must be organized in the format of a data set. To teach computers to recognize objects, we need to collect and organize and label images of every object in the world in as many variations as possible. ImageNet is such a data set with 22,000 image categories and over 14 million images. ImageNet is built upon WordNet to reflect the human representation of semantic meaning of image classes. It took thousands of workers on crowdsourcing platform years to build it. At the time of its release, ImageNet was the largest visual dataset in history by a wide margin. Now that we have the interesting machine learning problem to solve, and we also have the right kind of data, we can begin innovating algorithms. With the shared benchmark, every researcher can now explore and test their innovations to make machines recognize images accurately. For example, to understand there is a cat in the first image versus second image, we have a dog, and also trees, a motorcycle, etc. Algorithms built on top of ImageNet has advanced the state of computer vision considerably, with error rates steadily decreasing in the years since. ImageNet was a great contribution to the research field, but it's just the beginning. There are many more visual understanding problems beyond the image classification, which inspired a great amount of new data sets. For example, the COCO dataset and the visual genome dataset represent complex visual understanding problems, including image description and even more detailed understanding, such as object relationship and region-level description. These datasets inspired a great amount of research, including some of my own. In our research, we show that reinforcement learning, a critical method for AlphaGo to be the #1 Go player earlier this year, can also power complex visual understanding tasks such as image captioning. But dataset continues to require large amount of human labeling effort, which leads to the question of whether we can learn anything meaningful from large-scale visual data without human labeling. YFCC 100 million is such a dataset with 100 million photos and videos uploaded from Flickr, uploaded all over the world. We showed that it is indeed possible to learn meaningful visual model by leveraging a small, clean visual dataset and with the guidance of knowledge graph, such as Wikipedia, to guide the learning of large-scale visual data set from YFCC 100 million. Now we've talked about how computers could understand the image data. What about videos? YouTube 8 million dataset is such a dataset which extends the interesting visual understanding problem from static images to videos. YouTube 8 million dataset is a dataset with millions of labeled videos uploaded to YouTube. A corresponding video understanding challenge called YouTube 8 Million Challenge was hosted on Kaggle, who joined us earlier this year. Hundreds of teams participated in this challenge. And the winning team proposed a model to combine the visual model as well as the audio signals to tackle the problem of video understanding. And the result of the hybrid model works significantly better than any of the single model based on visual model only. As you can see, the result is listed in here. On the left, we show the ground truth of the video tags, such as vehicle and four-wheel drive, etc. And on the right, we show the top six scores predicted from this proposed approach, including car and vehicle as the correct prediction, and some of the fine-grained labels were mistake, highlighted in red. Video tagging and classification is just the start of video understanding. We also want to encourage research field to dive deeper on video understanding, such as object recognition and tracking in videos. At Google, we shared a new dataset called YouTube bounding boxes with thousands of labeled videos with bounding boxes tracked over time about the object's appearance. Video understanding is not just a simple extension of image understanding. It requires understanding of objects, activities, scenes, and events, and more importantly, how all these would evolve over time. Our field is just at the beginning of this direction. Much more research are yet to be developed. We've talked about how to generate the insights, how to organize data, and how to innovate algorithms based on the data. Now, the final step is to turn these algorithms into scalable and robust products that solve real-world problems. For example, YouTube has this interesting problem to automatically propose meaningful thumbnails for its videos. One big challenge for this problem is that thumbnail quality is subjective and most of the time depend on the context of the video. Fortunately, many YouTube videos come with carefully designed custom thumbnails uploaded by its own creators. Those thumbnails are typically well-framed, in focus, and centered on the main characters or specific subject of the video. We consider these custom thumbnails from popular videos as positive examples to the deep neural network approach, which is high-quality examples. And we also randomly select video frames as low quality or negative examples. Some examples of the training images are shown here. As a result, the trained model predicted the result of frames, and frames chosen by the new algorithm are preferred 60% of the time by humans. Video technology can also be used to enhance the video content as well as protect privacy. For example, video on the left showed us how video recognition or processing technology can help blurring the region of human as well as license plates to protect users' privacy. And video on the right shows advanced video processing technology to stabilize the video dramatically. As you can see, we've done a lot to make life easier for YouTube users, but the impact of AI is much broader than that. Now, let's talk about how this technology could benefit the real world. Seagulls are a risk species due to fishing and the coastal development. Conservationists have been trying their best to monitor them from the air, typically from an airplane window. But this is a very costly and inaccurate approach. For example, there is a seagull somewhere in this image, but I bet you'd have trouble spotting it. How long will it take for human to find where the seagull is? And imagine there are tens of thousands of images just like this, and how accurate that will be. A vision model built upon TensorFlow showed the incredible ability to spot the seagull. It's actually just right there. And it can easily scale up to tens of thousands of images. Another example is QP, which is almost a 100-year-old Japanese food company. To ensure the security and safety of their food product, QP depends on manual inspection of raw ingredients, which is a huge workload. For example, they have 30 to 40 people specially trained to take out contaminants among 4 to 5 tons of food every day at just one factory. To efficiently speed up this process, QP wants to train the algorithm, a deep learning algorithm, to find out which food is acceptable and which is defective. They do this by feeding over 18,000 images of little diced potatoes on the line of belt conveyor into TensorFlow. And the algorithm is able to pick out defective ingredients with near perfect performance. It dramatically reduces the repetitive work of the trained staff. Now they only need to inspect the results of the algorithm to ensure nothing slips through. Creative solutions like that tells us that AI can make a difference everywhere. We just need our imagination to lead us. The success of this process in computer vision can serve as a model for countless industries. We can replicate this process in different industries. We can start with the problem insights in the industry. We can then organize data to represent the interesting machine learning problem that is inspired from the insights. And we can innovate algorithms based on the data and the insights of the problems. And finally, we can develop products that can put the data and the algorithm to use. Cloud is in a great position of connecting diverse industries to potential AI solutions for them. It serves as a common platform to connect AI developers with customers in every industry following similar journey. First, similarly than before, we need to understand the challenge in each industry. We want to hear from the business leaders what are the typical problems, machine learning problems, and challenges are there in their field, and what are the creative ideas behind it. We then need to collect and process the data to represent the problem. There are two main approaches to solve the data problem. One is for existing data, how do we leverage the existing data, no matter if it's noisy or small data set? Interesting research topics could be how do we better leverage the noisy data to aid the learning. As I mentioned an example earlier. And another is domain adaptation. How to transfer the knowledge that we learn from one domain to massive amount of other different domains. But some of the data is rare by nature. For example, rare diseases and abnormal behaviors in videos. Some is too dangerous to obtain. For example, data from disaster. This leads to the direction of data simulation. And data don't always have to be created and collected from scratch. Google has shared a diverse set of data sets, including genomics public data and a YouTube 8 million data set with millions of YouTube videos. We're also happily sharing over 2,000 public data sets via Kaggle. For the scenarios which are challenging to obtain data, simulation is one way to obtain the necessary data. For example, in self-driving car technology, it's challenging to obtain abnormal events. But with simulators, you can obtain all kinds of scenarios by simulating them. As we talked earlier, there are many more AI problems beyond vision. With the right kind of data, we can explore algorithms based on them. The real challenge is to find the right kind of algorithm, whether innovating your own or tapping into existing algorithms via products. It's exciting to see ideas turn into real problem solutions. At Google Cloud, we're turning our advanced technology to impact and power external opportunities for our external customers. We offer a diverse set of products listed here, including tools such as TensorFlow and managed service built upon TensorFlow called the Cloud ML Engine. And we also offer a diverse set of APIs, from Vision API to natural language processing API to speech. And just as yesterday, we announced the Dialogflow chatbot API. The translation API is one of my favorite examples. Since switching from traditional method to neural translation last year, our translation accuracy get dramatically boosted. Here is an example how do we translate a Chinese sentence into English. Starting from first, each Chinese word is read until the entire sentence has been encoded in vectors. Then a corresponding English sentence is decoded, one word at a time. At each step, an attention function will tell the translator where to focus in order to generate the most relevant word. As a result, the gap between the machine translation and human translation is smaller than ever before. This has made a big difference for Vice. Every day, hundreds of articles are published on their platform across the world. But language barriers have been preventing the editors from understanding them all. Thanks to the translation API, now editors can browse every day's headline in their own language. And this allows them to instantly identify articles that are worth translating for their markets. Machine learning is also effective in understanding text. Google's Cloud's natural language API has the ability to automatically classify documents by domain across over 700 categories. This has made a big impact on Hearst Communication. Hearst Communication publishes over 2,000 articles every day across over 30 properties. By automatically grouping articles under categories like arts, law, health, layer, etc., it's now possible for editors to understand what topics are trending in real time. Our natural language API technology has also transformed the customer service for Ocado. Ocado is the UK's largest online-only grocery store. It accepts tremendous amount of feedback, all in the format of emails every day. This might make it to be easy for the customers, but it's a huge amount of burden for support staff. They are required to manually sort out all these emails. With Google's natural language API, each email can now be categorized and prioritized before it reaches the staff. For example, a thank you email is understood to require very little immediate attention, whereas a time-sensitive issue about a pending shipping is immediately given attention. Now, the support staff can focus their efforts where and when they are needed the most. We have seen many exciting machine learning use cases so far. Expert-designed models have solved many problems and generate great impact on numerous industries. But it took a lot of time and a lot of effort to get there. If we take only the problem of object recognition as one example, this is actually a very small area in the entire computer vision. Years of effort have gone into develop new models. especially since the first ImageNet challenge in 2010. It took a significant number of best machine learning experts from all over the world participating in competitions to invent the best algorithm to tackle object recognition. However, we're facing a real problem. There are just way too many distinct problems to solve one by one this way. While the models built over years of effort by the best machine learning experts work well on one problem, object recognition in photos. What about other problems? Like video understanding, satellite image analysis, image captioning, etc., etc. The best model working on the Google Photos won't work well for image captioning. We'll need a different model for every single type of data and every single type of new problem. How will we be able to scale the effort? Recently, however, a new approach has emerged. AutoML is a new way to automatically generate neural network architecture, rather than relying on machine learning specialists to write and optimize and tune parameters of machine learning models by hand. When AutoML was applied to the ImageNet image classification and COCO detection dataset, it achieved state-of-the-art performance. What if we can bring this to similar computer vision problems? AutoML is still very complex and it still needs a lot of improvement. But with additional effort to advance the methodology, it has the potential to accelerate other similar computer vision tasks. And this is just the beginning. But it's a promising glimpse of how we might use automation to design new machine learning algorithms in the future. This might help us to lower the barrier for machine learning technology and cover more scalable machine learning problems more quickly. Now, imagine in an ideal world, if we solve all these well-defined problems, then what? We still need business leaders to tell us about new problems that they observe from different industries. Let's explore a real-world example of the AI journey from the field of radiology. Chest X-ray analysis remains one of the most challenging radiological examination tasks. It requires extensive effort and expertise from radiologists to evaluate the results. The radiologists have to manually go through every single radiology image in order to come up with diagnosis recommendation. If we could build an AI-assisted radiology image analysis tool to assist radiologists, the entire process can be much more efficient. However, as many of us know, the supervised machine learning approach typically requires extensive data in order to train a machine learning model to recognize the signs of disease. Ideally, every single image needs to be carefully collected and evaluated in detail in order to train machine learning models. So there is a chicken and egg problem. On one hand, radiologists are spending significant amount of time analyzing radiology images to make diagnoses. An automated assistant that helps perform this task would therefore save their valuable time. But in order to develop the technology to power such an assistant, we need a massive amount of data to train the model. This, therefore, goes back to the exact problem that we want to solve. To solve this problem, we start with an open source dataset. The largest openly available dataset called NIH Chest X-ray for X-ray data. While there are a large amount of radiology data, which is over 100,000 X-ray images, each with up to 14 disease labels from the reports. This data is relatively easy to obtain directly from the reports. The dataset only includes less than 1,000 labeled bounding boxes for 880 images. This is placed by a board-certified radiologist. These bounding boxes help us to get more accurate result and information to train the model, but they require an extensive labeling effort. In other words, this dataset is not well suited for traditional supervised learning. Sorry. We therefore proposed a novel approach to jointly model the small amount of images with detailed annotation, detailed bounding box annotation, and a much larger amount of images with no manual labeling information. The resulting solution generates overall prediction of the disease type, as well as detailed reasoning and highlight of the suspicious disease regions. We demonstrate that this method produces significantly better performance than the state-of-the-art machine learning approach. We're just taking baby steps towards this direction. Significant amount of effort would still be needed in order to develop better algorithm and robust deployment in the future. Hopefully in the future, specialists can spend less time on repetitive and error-prone tasks such as basic diagnosis by working together with an AI assistant. AI is not a single technology or product. It is a journey that starts with fully understanding the challenge in some domains. And it will require us to collect and organize the data to represent the challenge or problem. And based on the insights and the data, we need to develop the right kind of algorithm to solve the problem. And finally, we need to put it all together to create a robust and scalable solution. We're just scratching the surface of AI. In fact, even a company as big as Google can only make a dent. I've been very fortunate in my career to participate and be involved in every step of this journey. I hope that my experience can inspire more people to join us by simply taking part in the dialogue. We need business leaders, researchers, and engineers all over the world to contribute to the space. We'll need to hear from business leaders about the challenges in different industries. We'll need to have engineers to participate in this journey, get up to speed with the largest tools and technologies to harness AI, and we'll need as many as possible researchers to get involved and contribute their algorithms and innovations in order to solve these problems in new domains. When everyone is part of this conversation, I believe there is no limit to what AI could achieve. I sincerely hope you'll join us. Thank you.
You go.
Oh, hi. Yeah, I have a question. As usual, very nice talk. The thing is, many of the problems here are focused on, especially in deep learning, on speech, text, images, right? Fabulous. Now, if you think of problems like robotics, so the type of things that Sergey and Peter are working at Berkeley, or a bunch of things, or you think of industrial problems, right? Industry 4.0. Optimizing PM cycles and yield and so on. So these have been studied in operations research and other areas, right? So you really have model-driven systems. So this integration of model-driven and model-free seems fairly challenging. And I'm somewhat curious about, in your type of environment, and if you think of cloud, automatic diagnostics, prognostics, remediation, provisioning could all be enabled by this combination of model-free and model-oriented. I'm sort of curious about your experience and where you're headed.
That's a very good question, also a very challenging one. So in the recent years in the AI field, we have seen effectiveness of supervised learning, data-driven, end-to-end type of machine learning approach. But there has been a large school of thinking, how do we combine knowledge and human experience with this data-driven approach. In my humble opinion, I really hope in the future there is a principled way to combine these approaches. Because from the human perception point of view, we don't need to read 1,000 images of cat and dog in order to learn what is a cat or what is a dog. We encode the knowledge implicitly and leverage that as future modeling power to predict what we want to recognize. So I really see the future would be a combination of knowledge model-free with data-driven, model-powered.
Have you encountered any successes at all in your local environment?
So there is some interesting research at its very early stage to combine very simple rules with bottom-up learned representation.
Thank you.
Yeah.
Thank you.
Yes. Very good presentation. To streamline all the steps. I just have a question regarding your auto ML and your you prepare your data. Seems to me it's include the prepare your data to categorize your all the algorithms. I don't know. I'm not quite sure what's your approach. I mean, for example, if your auto ML, I think you just treat the neural network as a black box. It's kind of a different way.
Yeah.
Yeah, could you give a little bit?
Totally.
Yeah.
So in the ideal scenario in the future, we hope, as I mentioned, AI algorithm could help us to prepare data, could help us to design the model, but it will take some time. In the current stage, the current research field, right now there is some early stage effort on how do we search the neural architecture space in order to come up with the best model. It's more focused on the model design instead of trying to assemble data and design model all together. But I really would be happy, very, very happy to see if there is research starting to handle large-scale noisy data or do domain adaptation. Meanwhile, can design a very good model based on that.
Yeah, I haven't heard about a lot of unsupervised learning. For example, in 90s, they have the memory association, this kind of the unsupervised. Does Google put effort on this one? And also for basically for your data or your picture tagging or the labeling, something like that?
Yeah, I think unsupervised learning, there are a lot of interesting research going on in the research community, both in the format or in the direction of learning the representation, as well as detecting anomaly or doing clustering of based on data observation. I think it's still a very, very important direction for us to follow. But at the moment, as you can see, many of the applications are effective based on supervised learning. We're just, usually research would start earlier than application, right? So we start to see a lot more effort in the direction, and hopefully in the future, there are more applications that can be developed based on mature technology.
Yeah, just quick, do you open all of your research, the resource, for example, the data to the public?
As I introduced in the talk, we open sourced the YouTube 8 million, and there is also the open image that we are open sourcing. We also publish and we put our papers online, so the methodology can be understood and perceived from those papers. We want to do more and more in this direction because we believe an open environment for basic research is going to advance both the industry as well as academic research.
I'm trying to pinpoint.
Thank you for the excellent talk. Very inspiring, especially after we have witnessed the disaster, the wildfire disaster in Northern California. I was thinking a lot of technologies Google already possessed could have probably detected the potential or imminent disaster as such. So do you see a possibility that some kind of integration of the different technologies in Google's portfolio could be put together and lead to a tool to avoid the next disaster as such?
I think that's an excellent question. This is exactly related to we really want to close the gap between the insights, the industries who has the insight, and the AI technologists.
Yes,
On one hand, AI technologists knows how to solve a problem, but they don't know what kind of problem to solve. What you provided is a very good example that we can see either image classification or some of the video understanding technology could understand what's going on from the disaster, but it's because of the gap that AI technologists probably didn't know, okay, there are these kind of interesting problems that we should solve, and it's going to be very impactful.
I believe Google has the technology today. Well, of course, I mean, unfortunately, we cannot have avoided a past disaster.
So I feel the field has a lot of great technology can be used for this kind of problem already.
Thank you. Thank you.
Hi, a quick comment and a question. The comment is, it's great that you brought up automatizing labeling data for training, for supervised learning, because absolutely for images, text, or anything else, having human experts label the data is not going to scale up at the rate that the amounts of data keep growing. And my question is with regards to your AutoML, how is it different, or is it fundamentally different from what's existed in meta-learning techniques when you are not sure which model works best and you use meta-learning techniques to pick one, except that, of course, meta-learning existed in theory for 20 years or so, and now computers are fast enough, the hardware is good enough to maybe accelerate this process. Can you comment on AutoML versus meta-learning?
I think in this topic, I'm specifically referring to the neural architecture search from our brain folks, from our brain colleagues. Basically, it's based on supervised learning, and it's based on, it is complex and would require significant computation to search the neural network architecture in order to come up with the best model there.
Sure, but how is that fundamentally different from mixture of experts, model selection? I'm not saying it's the same as bagging or boosting, but all these things that have been done in meta-learning, where you learn over learning models / algorithms to find the best.
I think fundamentally that's one shared big direction on how to search and using machine learning technology to select the best model.
Yeah. Hello, I have a quick question regarding medical diagnosis. So as you mentioned earlier in your talk, it took years for people to assemble images, to create ImageNet, and well, for neural networks to have close to human accuracy, they need to train on many more images compared to humans, right? So my question is regarding to diseases where there are only like a couple of thousand diseases a year or maybe tens of thousands of diseases a year, you simply don't have the data to train your neural network to make an accurate diagnosis. So I don't see how, in that case, we can assist medical experts where we simply don't have the data. So how do you plan to address that issue, especially in something like misdiagnosis? I mean, misdiagnosing a medical image, the consequences are far worse than misdiagnosing a cat with a dog. So.
Yeah.
Thank you.
I think that's an excellent question. As I mentioned earlier in the talk, some of the rare diseases, you just don't have that amount of data. And it's actually a fundamental question that as a field, we need to think about how to leverage a small amount of data, how to simulate new data to simulate the type of diseases. And also, how do we do effective transfer learning by learning from one domain or one type of disease that has more data and transfer that knowledge to more rare diseases. But this is still at the beginning, and it's an unsolved problem for the community.
Okay, thank you so much for the great talk. I'm a legal counsel here at Intel, so I'm going to ask a less technical but more ethical question. So we all know that the technology like AI has been transforming the autonomous driving industry, right? So more and more AI-related applications are used in the self-driving cars. So one of the ethical dilemma faced by all the self-driving cars, especially level 5, is who do you kill? So you have a pedestrian in front of you, and you have a giant car truck behind you. So do you kill the pedestrian in front of you or get killed by the back. So my question is more about, as an industry, how do we actually code or find the algorithm that's best help to solve this dilemma? I can take it offline. Thank you.
Very good question. I think there are two aspects of this problem or direction. First, we need to see that with the technology advancement, the accident rate is going to be dramatically reduced, which I feel pretty promising down the road. But second, I feel that's some question that we really need to work together with the the lawyers, as well as policy makers, and have everybody involved to generate, to develop really great technology that takes care of all kinds of human-centric type of problems. As technologists, we are not experts on this. We really need to collaborate with legal experts on it.
So we can make this the last question?
Sure. Yeah, I think in your presentation you mentioned that when you don't have enough data, you use simulation to obtain the data. So when you can simulate, you usually assume that you have an accurate or at least a physical model available, right? Mm-hmm. So you know, I just wonder, you probably see a lot of applications. So among all these applications, what people tend to, if I do have a physical model, mm-hmm. so I can attain the result, and what do you see how people use machine learning to kind of to get the result versus the accurate model to get there? I know the accurate model probably takes more time to simulate, but just look at this from all the applications you see. You know, what's the distribution that you know, and how. And the other thing is that my model that I use to simulate could be exactly the same, the thing that I want to figure out whether it's truly accurate or not, right? So if I simulate using a physical model that does not reflect the reality, then I could have a data set that is biased already.
Yeah, I think that's a very, very good question. Simulation has been a very long research topic already, but simulation in machine learning is still relatively where the researchers in machine learning and AI are still embracing the opportunity. It's at the beginning. Some of the data is easier to simulate. For example, for those that we have a lot of rules, for example, poker games and Go games, you can simulate all the scenarios from the rules, right? And there are more challenging scenarios. For example, robots navigating a space. We can build a 3D model about the spatial arrangement, but how exact and how accurate that will be, we can only approximate it. So it's a big topic that I feel it will be a future direction, research direction that AI researchers should put more effort on, given all these data rare cases and challenging cases to obtain data.
Thank you.
Okay, so let's thank our speakers. So let's present to you too, as this is a token of our appreciation. Okay, so we are going to serve dinner now. So for those who were here yesterday, you know the path. For those who were not, just follow the crowd. And we will be back here around 6.